All right, so let's move into differentiable functions for a second here. First thing's notation. If you're going to use function notation, and I'm going to be going back and forth between all forms of notation. So we have function notation. Is the first one. Function notation, if I have a function f of x, if I take the derivative of it, then we indicate it with a hash mark, okay, or exponent 1, I guess, if you want to draw it in that way. So it's the first derivative. If I then take another derivative, the notation goes to double prime, so it'd be a second derivative. Okay. If you're going to use the y equals format, okay, exact same. So y equals was the original function. Y prime is the first derivative. Take the derivative again. I have to indicate it with another prime. So now I've taken two derivatives. Finally, there's a third form, and it is Leibniz form. And this is the one that, from the Big Bang Theory, that Sheldon and Leonard dismiss. This is the German that some people say invented calculus. I mean, others say that Newton invented it. So there's a debate. But either way, Leibniz supported Newton's findings, or however you want to list it. I spelled Leibniz a little bit wrong. But anyway, he too came up with a little bit different notation, and we actually do go ahead and I do use it in Unit 4, so it is important. And it derives from the y equals format. So this is the original function, and then it is dy y by dy x, and really they're just d's with curvy backs. And if I take another derivative, then it would be dy squared y by dy squared x, and so on and so forth. So that's a Leibniz form, and there's a place for Leibniz form, and you're going to see it in Unit 2. All right? So moving down. So that's the notation that you're going to be seeing as we move through here. We say a function is differentiable. So that means that we can take the derivative. What does derivative mean? It means that we can find an expression for slope of a tangent. So it's differentiable if the function is continuous. A continuous function, again, is a function that you can draw without lifting your pen or pencil. And the other part to that is there's no abrupt changes in slope. All right, so I have a couple of examples down here if you want to sketch yourself out 3 rough xy axes. So the first one, if we have a piecewise function. So a piecewise function might look like this. Okay, we have abrupt changes, we have breaks. So the only way that I can trace this graph is by lifting my pen or pencil here. I then have to lift it again here. So in 2 locations, I have to lift it. So this is not a differentiable function. We can take the derivative of a section of this function, but we cannot come up with one expression for the whole function. Okay, but we can take the derivative of parts of the function. Next is that severe change in slope. So an absolute value. This is what we call, down here at the elbow, we call this a kink. Okay? We cannot take the derivative of functions that have kinks, and that's because the abrupt change in slope. So an absolute value function we cannot take the derivative of, but you can take the derivative of one side of the kink, and you can take the derivative of the other side of the kink. So you can do it by parts. And finally, if we have an asymptote, okay? So the asymptote function look like this. Again, you have to lift your pen or pencil if you want to draw this graph. The asymptote creates a break. Okay? So we cannot take the derivative when there is that gap in the function itself. We can take the derivative of parts of it. Okay? So we can take the derivative of the right side, the derivative of the left side, but we can't come up with one uniform notation. So power and sum difference, the power and sum difference rule. So yesterday you did an investigation, and I'm just going to go through and do 2 of them from first principles, and then so I'm going to, as an example for your note, So I'm going to take the derivative of y equals negative x squared plus 1. And then I'm also going to take the derivative of y equals x cubed minus 4. So I'm going to pause the video right now. I'm going to go through and do the work on that and do it from first principles so that you can see the pattern that you saw, or just so you have that pattern written down in your notes. Okay, so as you rejoin me, you can see that I took found the slope, or an expression for slope, from first principles. So this is very similar to the investigation that you did earlier. And what we find are the key things that I want to look at specifically here. We started with negative x squared plus 1, and now we're looking at negative 2x. Similarly, we had x cubed minus 4, and now 3x squared. Hopefully yesterday from the investigation you concluded that there was a relationship that exists there, and the summary should have looked something like this from yesterday. From a polynomial, f of x, the degree of the resulting slope was 1 less than the original function. And the second one, the original function f of x, had the exponent on each variable multiplying the coefficient. Or somewhere along those lines. So that was comma, I guess, and the exponent decreases by 1. And that's what I was hoping that you would pick up from that investigation previous. All right. All right, so moving along then. We come down to some rules for derivatives. All right, so the first rule I want to talk about is the constant rule. So if we have a function f of x that's equal to some number, so we're going to call it c, f prime then of x is going to equal 0. So if we take the derivative of a constant, it's always going to be 0. Why is that? Well, what does a function look like that's a constant? Well, here is f of x equals 2. What is the slope of the tangent line? Well, anywhere along that line, the slope is going to be 0. So that means it doesn't matter where you are in the graph, slope of tangent line is equal to 0. Our power rule. If the original function f of x is equal to ax to the exponent n, f prime of x will equal n multiplied by a, x to the exponent n minus 1. And that's from that investigation that the degree of a polynomial, that's what we're dealing with, is polynomials. If I have a quadratic for my f of x, I know that the resulting function, or the derivative, the graph of the slopes, is going to be a linear function. All right? So the degree decreases by 1. What happens if we have negative exponents? So if my original function is equal to ax to the exponent negative n, that means that the function, the exponent, is actually going to get more negative. So f prime of x equals negative n times a. So the coefficient's going to change signs. And the exponent, because it's negative and you're still taking 1 away, it's becoming more and more negative. And finally, rational exponents. So what happens if we have a fractional exponent? So m over n. The derivative would be m over n multiplied by the coefficient. So you're multiplying the coefficient by the fractional value, and x to the exponent, and you're subtracting 1. So you just, whatever the fraction is, you're going to subtract 1 whole part from that. So there are your general rules, and that's what we call the power rules, okay? Or I guess any of the rules dealing with polynomials. So, examples. Just got a couple of examples. Find the expression for slope. Okay, and I got a couple minutes to do an example here. So for number 1, if our original function f of x was equal to negative 2x to the 105, the derivative would be negative, double that, 210, x to the exponent 104. So the exponent decreased by 1, and we multiplied the coefficient by the original exponent. What about 4x to the negative 6? So the exponent multiplies the coefficient, so 4 times negative 6 is negative 24x. Take 1 away from the exponent, and just be careful, it's going to get more negative. So you would subtract by 1. 3, what happens if we have f of x equal to 3 over x squared? First thing you want to do is you want to get rid of the fractional part. So I'm going to rewrite it using my exponent laws. So that's 3x to the exponent negative 2. My derivative then would be negative 2 times 3. It's negative 6. X to the exponent negative 3. What happens if it is a longer expression? So for example, f of x equals 2x to the 4th minus 3x cubed plus 7x to the negative 1. You take a look at each component and you take the derivative accordingly. So 4 times 2, so we would have 8x cubed. Moving to the next term, 3 times negative 3 is negative 9x squared. 7 times negative 1 is negative 7x to the exponent negative 2. And the last example, what happens if we have radicals? So f of x equals square root of x minus the cube root of x to the 5th. Your first step is to rewrite this without the radical sign. So we have x to the 1/2 minus x to the exponent 5/3. Now we can take the derivative. Coefficient and exponent get multiplied. 1/2 take away 1 is negative 1/2. The next one would be negative 1 times 5/3. So we'd have negative 5/3 x to the exponent 5/3. If you take away 1 whole, so 3 over 3, you're left with 2/3. Okay. So there are some simple examples. That's about the level of difficulty we're starting with here. So it's just practicing with our power rule and then moving on. And you have some adding and subtracting. But basically with the adding and subtracting, you are treating each term or taking the derivative of each term when adding and subtracting. Okay? If you have any questions, please make sure you ask and I will attempt to clarify. And, oh, before I forget, your homework too, you'll have that in front of you at some point, but there's the homework that's assigned for this particular section.